Okay, in this example problem, I'm dealing with a wireless signal with a radio frequency of 2.4 gigahertz. Guess what? That's Wi-Fi. It's your standard channels 1, 6, and 11 on Wi-Fi. 2.4 gigahertz and acts as a carrier wave for an 11 megabits per second signal. In fact, that is one of the old speeds of 802.11. Most of our speeds are 54 megabits per second or higher nowadays. But 11 megabits was one of the earlier standards. I think that's 802.11b. And it says, what is the length of one bit of this signal for part A? What is the wavelength of the signal? And how many wavelengths of the carrier wave per bit in the digital signal? Okay, so the idea here is that we have a traveling wave with a given frequency. And we know that that traveling wave goes a certain distance in a certain amount of time. And we have an 11 megabits per second signal. So we can calculate the bit period. And once we calculate the bit period, then we can figure out how far the radio wave went in that bit period, and that would be the length of one bit. So let me do that first. For part A, we're going to say that we're going to take the numbers that we have, first of all, and translate them into the symbols that I showed in class. RB is the bit rate, and this is 11 megabits per second, and this is 11 times 10 to the 6th bits per second. Okay, and we also know that the speed of light propagation of this radio wave is 3 times 10 to the 8th meters per second. What I'm going to do is I'm going to calculate the bit period and then calculate how far the wave went in that bit period. The bit period is 1 over the bit rate, so it's 1 over 11 e to the 6th. And I type that in on my calculator. 1 divided by 11 times 10 to the 6th is equal to 9.1 times 10 to the minus 8th. And that is seconds. Okay, and I'm going to leave it in seconds, and I'm going to say that the length of a bit, what I'm going to do is I'm going to use the distance is velocity times time, and so the length of a bit, the distance that the wave has gone during one bit is c times t bit. And this is 3 times 10 to the 8th times 9.1 times 10 to the minus 8th. And so we end up, the 10 to the minus 8 and 10 to the minus plus 8 cancel, and I get 3 times 9.1, and I guess that's 27.3. And that is going to be in meters because c was meters per second and t was seconds. Okay, so it's 27.3 meters. So the wave went 27.3 meters during the time it took to have one bit. Okay, and that's what we call the length of a bit. For part B, what is the wavelength of this signal? Well, now we're talking about the wave, the electromagnetic wave. We have the frequency of 2.4 gigahertz, and the period, t, and this is different from the other t here. This one we put a subscript b on for bit period. This is just the period of a sine wave, and this is 1 over f. And let's see, 2.4 gigahertz is 2.4 times 10 to the 9th hertz, or 2.4 times 10 to the 9th cycles per second. So the bit period is 1 over that. And if I type that in on my calculator, I get 1 divided by 2.4 times 10 to the 9th. And this comes out at 4.17 times 10 to the minus 10th. And this is in seconds. So that's the period. Let's see here. What am I doing? I'm supposed to be calculating the wavelength of this thing. And what I'm going to do is I'm going to use the fact that the speed is equal to the distance divided by the time, which is the wavelength divided by the period. Okay? And I need to then solve for the wavelength here. So I'm going to say lambda is c times t. And so lambda is 3 times 10 to the 8th, 3.0 I guess there, times the period, 4.17 times 10 to the minus 10th. So I'm going to take the answer that's sitting here on my calculator already, times 3 times 10 to the 8th, and that equals 1.25 times 10 to the minus 1. In other words, 0.125. And that has units of meters. If you're keeping up with this, you may notice that I could have simply said that C is lambda F and not calculated the period at all. I like to use C equals lambda over T because it really makes it clear that we have a distance divided by a time, and that's a speed. Okay, but I could have just taken 3 times 10 to the 8th and multiplied it by F, and I'd get the same thing. In other words, the wavelength of your wireless Wi-Fi signal is 12.5 centimeters. Okay. Finally, it asks, boy, we're running out of space here. Finally, it asks us to calculate how many wavelengths of the carrier wave per bit of the digital signal. Now this problem actually is a bit tricky because it's combining a Wi-Fi sine wave with a digital signal, okay, that's imposed upon that sine wave. And we're going to see how we do that. We haven't studied that yet this semester, but we're going to see how we get our digital signal onto that Wi-Fi sine wave. But for now, what we can do is we can calculate how many wavelengths are on a bit of the digital signal. And it turns out that the number of wavelengths, n, per bit, what we can do is we can take the wavelength of the signal and we can divide it by the length of a bit. Okay? We can also plug in these equations. Lambda is c times t over here, and LB is c times TB. And so we have c times t and c times TB. In other words, the c's cancel, and the number is also the ratio of the time, the period of the sine wave divided by the time it takes for 1 bit. Actually, we're going to get a very small number here because t is 10 to the minus 10th, whereas t bit is 10 to the minus 8th. And I've actually calculated this number upside down. I'm going to put a minus 1 here, and I'm going to go ahead and plug in, and we'll see what we get here. 4.17 e to the minus 10 all over 9.1 e to the minus 8. And this comes out to be, I did start writing it upside down, times 10 to the 10th. .17 times 10 to the minus 10 divided by 9.1 times 10 to the minus 8 is equal to 4.58 times 10 to the minus 3. And if I want to calculate the number, then I have to invert that and hit the 1 over x button, and I get 218. And so what that shows is that there are 218 of these wavelengths on the Wi-Fi radio wave for every 1 bit on our digital signal. Okay, and hope that helps. Sorry I put this number upside down. Basically, we're looking for the ratio and how many wavelengths of the carrier wave per bit, and it turns out there are 218, and I made the ratio of the wavelength of the carrier to the length of a bit, and I should have done it upside down, but it doesn't matter. We can put a -1 here and just hit the 1/x button when we're done. Okay, hope that helps.